Welcome, as I said, to the June 2024 Soils Network of Knowledge webinar on nitrogen fertiliser use and greenhouse gases by Rob Norton and Peter Grace. Now, great pleasure to introduce Rob and Peter. So firstly, Rob will be the first speaker and then it'll be to Peter. Rob Norton has expertise in crop nutrition, farming systems and agronomy. He worked in education, graduate training and research with the University of Melbourne, where he holds an adjunct position. Following a role as Regional Director of the International Plant Nutrition Institute, he has been engaged in soil fertility projects in Africa, as well as local consultancies to a range of public and private organisations. Rob holds a PhD in crop agronomy and has authored 150 refereed scientific publications, as well as many more articles for industry. On his so-called retirement from full-time employment in 2018, his contribution was recognised with awards from the Grains Research and Development Corporation and also Fertiliser Australia. Peter Grace is Professor of Global Change at Queensland University of Technology in Brisbane, Australia. He has over 30 years international experience in soil nitrogen cycling for sustainable agricultural production and greenhouse gas emissions. He was previously Senior Soil Scientist at CIMMIT, and he led the National Agricultural Nitrous Oxide Research Program, or NANORP, in Australia, and is involved in the Global Research Alliance for Agricultural Greenhouse Gases. He also holds an adjunct professorship at Michigan State University. So, Rob, I am now going to offer you to take over as presenter.
Thanks, Luke. Thanks for the opportunity, and it's great to share the stage with Peter Grace, who we've known for a long time. And part of what we're going to talk about today is based on a publication that Peter and myself, Cameron Gooley from Victoria, and Jeff Clark put together for the fertiliser industry based on nitrogen fertiliser use in greenhouse gases, an Australian assessment. And this is the publication that was referred to and linked in under the publications handout section on the control panel. So you can have a look at that. There's a longer version and a not so long version, but it's still long. But essentially what we're trying to do is establish some of the parameters about nitrogen fertiliser use. And today is a quick run through some of those issues. The first question, I suppose, is why nitrogen? What's so special about nitrogen? Well, nitrogen is the essence of life. It's in every cell that we have as DNA, and it's the proteins that drive the energy in our muscles. And nitrogen itself, dinitrogen, is abundant in the atmosphere. 78% of the atmosphere is dinitrogen, but reactive nitrogen, which I've indicated as NR, is scarce. That's nitrate, ammonia, etc. We use a lot of nitrogen fertiliser. We use globally 109 million tonne of nitrogen fertilisers. In Australia, we use probably nearly 200 million tonne of nitrogen, 65% on field crops. Most of that is urea. And it's not an academic exercise. The purpose of using nitrogen fertilisers is to grow food. And not just nitrogen fertilisers are used. We use fixed nitrogen. We use nitrogen from manures and composts, and we also use nitrogen from the soil as well, from soil organic matter. So those nitrogen flows into food have some issues about diversions into nitrate, leaching away, causing soil acidification. We're going to specifically consider today nitrous oxide as a greenhouse gas. We also have ammonia ending up as PM2.5, causing some health problems, and nitrate and ammonia transfers causing ecosystem disruption when they're redeposited on areas that are used to having very low nitrogen status. So those are concerns. While we use a lot to grow food, there are concerns over those lost processes, those flows to land, air and water. There's also concerns equally with insufficient nitrogen leading to soil organic matter degradation and low food production. And I think both of those things represent a balance in the way we need to review nitrogen management. It's been an issue of global interest through, for example, through the UN Sustainable Development Goals. identify issues around food security and environmental integrity, not necessarily specifically related to nitrogen, but nitrogen relates to those SDGs, Sustainable Development Goals. We've also got organisations like the Global Partnership on Nutrient Management, which is part of the UNEP, the EU Nitrogen Expert Panel, and of course the industry organisations like IFA, International Fertiliser Association, and in Australia, FertCare. One of the publications that is worth looking at is Our Nutrient World, which provides a framework. It's 10 years old now, but it provides a framework about some of the issues relating to nitrogen management. The reason we wanted to write an Australian view is that our situation in Australia is very much different to a Eurocentric view of, or a North American-centric view of nitrogen. Nitrogen 101, what's the fate of nitrogen? Where does it come from? Where does it go? And I think this is fundamental to understand where we're going with in terms of nitrogen and nitrogen use efficiency. When we talk about nitrogen use efficiency, we talk about nitrogen fertilisers going in and products removed as outputs, and that becomes what we call nitrogen use efficiency, input and output. There are some loss processes I've mentioned. There's loss processes with things like ammonia volatilisation, nitrous oxide and dinitrogen production due to denitrification. And there's also leaching and runoff of nitrate from the soil and from the surface of the soil. Some of those ammonias and some of the nitrous oxides are redeposited, and that's where we get the issue with ecosystem disruption, as well as from leaching and runoff. With the nitrogen ending up in unintended environments. We've also got a major input of nitrogen through crop residues, some legumes such as in Australia, lentils, chickpeas, field peas, beans, etc. They all provide nitrogen input. It's not just fertiliser nitrogen. Manures, crop residues, etc. all provide input into that nitrogen cycle. In terms of the losses or the unintended areas where nitrogen might end up. If we think about, say, for example, ammonia, very big ballpark figure, maybe 10% of nitrogen ends up volatilised, mainly from nitrogen fertilisers, and again, mainly from urea, but other ammonium-based fertilisers also result in ammonia volatilisation. We get maybe 10% leached. And both of those things depend, the magnitude of that loss depends entirely on the environment and the soil types and the management strategies deployed. But today's star of the show is nitrous oxide and the processes involved in generating nitrous oxide from nitrate, not just nitrate, we'll talk later, Peter will talk later about some of the issues, but the amount of nitrous oxide produced in relation to nitrogen input might be 0.2 to 5 to 10 to 20% of nitrogen. We call that the emission factor, how much of the nitrogen input ends up as nitrous oxide in particular, because that's the main greenhouse gas that we're concerned about. And there's lots of pressure on nitrogen as a source of greenhouse gas. Australia and agriculture contributes about 16% of Scope 1 emissions, and nitrous oxide emissions are about 16% of ag emissions, so 16% of 16%. And those fertilisers contribute through direct emissions from fertiliser application to 2.5 million tonne of carbon dioxide equivalent, nitrous oxide through indirect emissions, so that's nitrogen that's redeposited and re-evolved as nitrous oxide from dung and residues, about 8 million tonne. And there's also CO2 evolved when urea hydrolyses. Urea, the central atom in a urea molecule, is a carbon. That carbon has come principally from fossil fuels in the Haber-Bosch process. And so that's a fossil fuel carbon. It's not a nitrous oxide emission, but it's a carbon dioxide emission. There's also additional scopes, what we call Scope 3 emissions from nitrogen fertilisers, which are a consequence of the production process. They're not directly included in our greenhouse gas accounts, but the amount of energy that is used to produce urea in particular and nitrogen fertilisers in general is significant, and you can see the number there of about 5.5 million tonne of carbon dioxide. And the range depends on where the fertiliser is produced and to which feedstocks are used, whether it's coal or gas, And the opportunity, in fact, is to have green ammonia production using renewable energy. So that's just a bit of what the pressure is on nitrogen as a source of greenhouse gas. So what can we do to reduce this pressure? Well, pretty simply, there are two directions: using nitrogen efficiently, which I'll discuss, and secondly, reducing nitrous oxide emissions from nitrogen fertilisers specifically, and Peter will discuss some of those. There's also quite a lot of interest in green ammonia, as I mentioned just before. We won't particularly cover that, but certainly it's something that is of great significance to us because we have such great solar and wind resources to generate electricity and produce ammonia by electrolysis. I think that Australia is well placed to exploit the opportunities around green ammonia. So in terms of reducing the pressure that we have on nitrogen, and the key is to use it as efficiently as we possibly can. And that means looking at input and output relative to each other. And that's the most common nitrogen use efficiency term, which is considered as the removal divided by the input of nitrogen fertilisers, or it might also be consider an estimate of fixed nitrogen or removals of nitrogen from the soil and or removals of additions of nitrogen supplied from manures and composts. This is called a partial nutrient balance, but in our documentation, we just called this nitrogen use efficiency simply to give a simple term. And of course, a simple term misses a lot of the nuances, but as a ratio between input and output, it gives us a relatively useful value. Some of the values that we've calculated, say for cereals in Australia, 20 million tonne, there's about 461 kilotons of nitrogen removed in that. In terms of what the nitrogen use efficiency, we're operating in that wheat scenario at about 97%, other cereals at about 68%, 88% for oil crops, and for cotton and sugar, relatively low. There are great industry differences between potential for efficiency values. We like nitrogen use efficiency because we can scale it from field to farm to region to country, and we can measure that reasonably easily over time. And we've done some of that, and we'll identify some of that in a moment. But as a simple measure, it has to be interpreted very carefully, and just saying 97% or 48% really hides a lot of the issues that we need to be careful about considering. It's useful to consider Australia in an international context too. The European Nitrogen Expert Panel developed a protocol which looked at nitrogen input, nitrogen output, nitrogen removal, and drew a line of 90% nitrogen use efficiency and 50% nitrogen use efficiency. If your nitrogen use efficiency is above 100%, there's more nitrogen removed than supplied, so there's a risk of soil mining. If nitrogen use efficiency is less than 50% or even less than 100%, there's more nitrogen unaccounted for than removed, and there's a risk of that environmental damage, whether it's from nitrate leaching, nitrous oxide, ammonia, volatilisation, or whatever. We looked at this framework and wanted to look at where we sit in relative terms to these other countries. Interestingly enough, this system was devised by the Europeans, and they set up these 50 and 90. Maybe we can discuss whether 50 and 90 is appropriate. Curiously enough, European Union sits right in the middle of a very nice, what they say is a target zone. Australia is right down here. We're very modest nitrogen users. We have a very good overall, this is for cereals, by the way, we have a very modest nitrogen use, maybe 44 kilograms of N is about normal, and we're about 83% of nitrogen use efficiency in cereal production systems. So in a global scenario, we're right at the bottom of these top 20 nitrogen users. That doesn't mean we're out of the woods. We did some surveys of paddocks. We looked at paddocks, over 500 paddocks over 3 to 4 years in southeastern Australia. And we also looked at the balance of those paddocks. And this spotted graph here gives us an indication of where we'd find each of those paddocks. And the different colours refer to whether it's high rainfall, low rainfall, medium rainfall environments, but it doesn't really show up very much in terms of the difference. So what we do come to the conclusion is that of those 500 grain paddocks, 34% had a nitrogen use efficiency less than 100. So in fact, less than 100 means the risk of environmental damage. But more concerningly, 50% of those paddocks had a nitrogen use efficiency between 100 and 200, and 14% had a nitrogen use efficiency greater than 200. So that 64% of those paddocks were actually mining soil nitrogen. Where does that soil nitrogen come from? Well, it comes from soil organic matter. So in one sense, we think about this as being underuse of nitrogen. Whether that situations change, we need to keep doing these numbers, and I recommend that advisors do some of these assessments with growers just to see where they're trending. And the opportunity is to lower high nitrogen use efficiencies and raise low nitrogen use efficiencies. And I think that is the sort of message that we can do that. It's within our wit to manage that nitrogen use efficiency. So what are the strategies? Well, the fundamental strategy is good agronomy. Sowing a crop on time, using the appropriate cultivars, making sure pH, acidity, salinity, organic matter levels are all appropriate for the crop and the environment we're working in. And within the fertiliser management side, we'd be thinking about the source, rate, time and place, which we call in IPNI 4R nutrient stewardship. And they're the levers that we would be pulling in terms of managing nitrogen use efficiency. And anyone who's sat in a modern header these days realises that there's more buttons and levers and switches to pull and push than you could ever imagine. But there are some simple guides about how we can manage source, rate, time and place to make the best outcome in terms of nitrogen use efficiency. We don't really have time to go through all of these issues, but in terms of source, rate, time and place, in terms of sources, we can use organic sources, compost, manures, crop residues. In fact, we already use crop residues in a stubble retention situation, nitrogen cycled through the stubbles. We use biological N-fixation through pastures and legumes. We can use enhanced efficiency fertilisers, and Peter will talk a little about some of those opportunities, not just in terms of nitrous oxide, but in terms of managing and maximising the efficiency which nitrogen gets into the crop. In terms of rate, managing the rate is probably one of the most important things, and it's the thing farmers focus on very much, rate matching to match the demand of the crop. We can slightly lower rates, and that has a large effect. It doesn't have a large effect on yield, but can have a large effect on loss processes such as leaching, acidification and greenhouse gas production. Including other sources such as mineralisation and immobilisation in our rate calculations is something to consider as well. Timing, growers would be very familiar with matching timing of nitrogen by splitting, using foliar applied fertilisers, using controlled release fertilisers, which are part of the family of enhanced efficiency fertilisers, and avoiding times when losses are likely to be high. We look to place fertilisers where the roots are active. One of the greatest strategies, I think, is using paddock zoning, using remote sensing or whatever proximal sensing, soil type assessments to match the placement of fertilisers with areas where the highest demand is, and applications to meet the target rate. So with that very quick, brief overview, I'll hand over to Peter, who will discuss reducing the pressure about nitrous oxide emissions.
Yeah, hi Rob, thanks for the handover. I hope everyone can hear me. Thanks for the detailed input from Rob in terms of nitrogen use efficiency. It has a big impact on your profitability when fertiliser prices change markedly, as they did a year or so ago. And the fact that now we have this whole greenhouse gas discussion going on, and whether decarbonisation of the farming industry is necessary, which in some terms it is, keeping the emissions low. And I'll put nitrous oxide into its context shortly, but just talk here quickly about what causes denitrification and where does nitrous oxide come from. Nitrous oxide, it's a small amount of the N that you actually apply as fertiliser. It may be 1/100th, it may be less, But on the other hand, it has a big impact in terms of its effect on the atmosphere as a greenhouse gas. But let's just talk about nitrification and denitrification generally, the two major processes in soils where mineral nitrogen is converted into other forms, whether it's a gas or whether it's another mineral form. And you can see here the equations. Nitrification, that only happens in drier situations, and that's when you would apply your fertilizer initially, say urea. It hydrolyzes and then it'll nitrify, and then that nitrify means you have nitrate forming, NO3. That's the one we're really after when it comes to keeping in check, when it comes to denitrification. And denitrification only happens when you have a wet soil profile. All of these are very dynamic, and it doesn't happen like slowly, it happens very rapidly. They're very episodic events, these gaseous losses. If you look here in the top right-hand corner, the graphic here, water filled pore space on the x-axis, that means you're increasing in water content, and 60% is about field capacity. 80% you're getting closer to saturation, 100% means saturation. And on the left-hand axis, it's saying the flux of gases. That means how much of the gas is being actually emitted. As you can see, there are no absolute numbers, just a graphic to show approximate differences, relative differences. But as you can see here, where you have at field capacity, you're getting some nitrous oxide emitted from nitrification. And then once it wets up, getting more towards the 80%, so there's been rainfall events or irrigation, you're still getting nitrous oxide, but then this oxygen on the nitrous oxide is consumed by the microorganisms and you start getting N2. Now, N2 is what our atmosphere is. So I think it's 70% of our atmosphere is N2. It's totally inert. So this N2, whilst it's quite large, when you have a denitrification event on, say, a clay soil, it's an agronomic loss. It's an economic loss. It's not an environmental loss, as is nitrous oxide. Here's an example of a field. Here's some data going from September to October. There's been a denitrification event. You can see the water lying here, and you can see ammonia. You're still having ammonia being produced, but look at the big change in nitrate. It's gone from 120 to 25. And what that means is you've had a big denitrification event. I just want to put nitrous oxide in context. A lot of the work and where all the rural industries are heading is around greenhouse gas accounting, carbon accounting. And here's an example of, on the right, a well-managed field under no tillage. This photo is 20 years old. And you can see what I've got here is just giving you relative magnitudes and what's happening. In this field, you're actually getting sequestration of carbon dioxide. That's the most common greenhouse gas that you hear about all the time. The other greenhouse gas is methane. There's some of that in the atmosphere. Some of that can be taken up in these aerobic systems. Again, aerobic, well drained, and then only a little bit of nitrous oxide may be bled out of the system. So that's a well-managed system. You're actually sequestering carbon. Your carbon account is actually pretty neutral because you've got to add all these numbers up. Over here, a poorly managed site, conventionally tilled, residues may not have been returned. Again, rainfall event, the same rainfall event has been over here on the left across the fence. And there's an enormous amount of N2O released. Relative to the other field, there's a large amount released. And then CO2 in small amounts and methane a little bit is potentially emitted. But methane normally comes from rice cultivation. And I assume on the left, if it was like that for too long, you would be putting it under rice. Now, I want to put those three gases into context. The next slide will provide that information. So the main reason about this is because nitrous oxide has a high global warming potential. It's 270 times the global warming potential of CO2. So whilst you read everywhere about CO2 being reduced and that, This is why nitrous oxide is such a bugbear in the agricultural industry, but particularly where fertiliser is used. One molecule of nitrous oxide is equivalent to 270 molecules of CO2 in terms of its impact on the atmosphere, in terms of its warming effect. So we really need to get on top of nitrous oxide. Yes, there's a lot in the literature and there's a lot out there in the industry about sequestration of soil carbon. Yes, critical for soil health, critical for fertility, critical for structure. On the other hand, nitrous oxide is the real target we need to be going after. That calculation, when you hear numbers being thrown around about carbon dioxide emissions from agriculture, it includes all of those gases as a single term called CO2 equivalence, CO2e. And that's how you calculate it out. You have to include these global warming potentials to come up with that number. So it's a common currency. Again, you've seen something similar to this earlier on. There are two we call sources of nitrous oxide, general classes of sources. The direct sources, again, fertiliser is applied, any nitrogen source at all, fertiliser, urine, dung, manure, legumes, crop residues, anything that has any nitrogen in it is classed as a direct nitrogen source where nitrous oxide can be emitted. So that's how we determine these emission factors, which is the proportion of nitrogen that is that is emitted as a function of how much you've actually added. So nitrification, I've already mentioned, nitrous oxide, you get a bit of a bleed, and then denitrification, you have nitrous oxide at not as much as N2. On the right, there's a graphic, and you can just see, you're going to think, well, why are we after this number all the time? It's so small. Again, as I've tried to get across to you, is that it is a highly potent greenhouse gas. It has a big impact on climate change. The blue line is your agronomic loss in terms of N2, whilst your yellow line is your environmental loss. But multiply that yellow line out as CO2, it blows the N2 away in terms of its impact on the environment. We also have what we call indirect emissions, and again, you can control these partially by getting a handle on volatilization, and then you have leaching. Okay, both, again, these are excesses. Ammonia is lost if you're not managing that application of fertilizer properly. Okay, if you're leaving it on the surface and it's wet and dewy, and you have an alkaline soil, you'll lose a bit of through volatilization, but you've got to manage that. Leaching, same thing, a bit harder for you to manage itself, but if you have excess nitrate in your profile, it's normally in the sandier type soils, loamy sands to loam. You don't get a lot of leaching in the clays. You might get some leaching through the large pores, macro pores, cracking clays, but leaching is more so in the sandier soils. Volatilization you'll find more in the alkaline soils, and denitrification, which is what we've already been talking about, that happens more in the clay soils. So this gives you just a rough idea in terms of if you're doing an account of your nitrous oxide to the atmosphere, where's it coming from? Fertilizer is normally the main source, but again, really depends on how much you're applying. Indirect emissions, and then crop residues itself. That value in terms of emissions on crop residues, we're doing a fair bit of research on that at the moment. That may come down. Give you an idea here, the driving force behind this, as you know, not just the nitrogen that's applied, it's water. So annual rainfall, here's some data we've picked up over many years. Again, look at the y-axis. These numbers are low compared to what you've applied. 0 to 16 kilograms per hectare. That's low compared to the nitrogen actually being applied, and you can see that on the x-axis. But increasing in rainfall, there's more of potential for denitrification, and a lot of these studies have been done on, we've concentrated our research on the clay soils as well. Okay, so if you go to Western Australia, rainfall about 300 to 400 mils per annum, their emissions are zero because they're on a sand and it's basically no potential for denitrification. But you can see here the cane industry, yes, high rainfall and very high emissions. Where do we get these numbers from? Again, there's been a lot of research done in the past, and there continues to be, and there will be a reinvigoration of research into the future through the Cooperative Research Centre for Zero Net Emissions in Agriculture. We actually go out and measure on farm these emissions. You can see all the different chambers that are used. Again, a very highly specialised research, but again, the data has shown that Australia is at the forefront of nitrous oxide research for its farmers. What I'm just trying to show here quickly is nitrous oxide is dynamic. Unlike soil carbon, which will accumulate slowly over time, like annual changes, and it's not a rapid change when you talk about soil carbon accumulating, nitrous oxide is highly episodic, and that's the nature of the nitrogen cycle. Things are happening on a daily basis. And here, if you just look at the blue line, that's changes in water content. And you can see on the y-axis, water-filled pore space on the right. And the higher it goes, it means there's more moisture in the profile, up to 100, which means saturation. And you can then see the emissions happening when if you look at maize, for example, you can see the increase in soil moisture, and straight after that, the soil water content going up, a big flux of nitrous oxide emissions. And again, they linger on for one week, maybe longer. So this is a great example of the dynamic nature of the nitrogen cycle. And that's why there's so much work going into how we can manage our nitrogen inputs and how we can manage our losses, and how difficult, I have to admit, to increase nitrogen use efficiency. So the official numbers that are used in the Australian National Inventory. So the Australian government every year reports this to the international community, okay? And these are the different categories. And the emission factor, again, is, for example, kilograms of nitrous oxide nitrogen emitted per kilogram you have applied per hectare, and that's a percentage, so you multiply that by 100. But you can see here, the majority of these numbers are less than 1%. And you think, why? Again, I've already demonstrated the high global warming potential nitrous oxide has. So these small numbers actually become very big numbers when it comes to the environment and the impact on the environment. You can see the grains industry, generally 0.4%. That varies between the low rainfall, high rainfall areas. Irrigated crops, cotton, sugarcane is the one that tends to stand out, and obviously more research has to be done in that area in terms of reducing emissions. This is a generalized map, and believe it or not, I drew this not the map of Australia on the outside, but I drew the boundaries by hand because it was the easiest way to do it a few years back. But you can see these are just some of the sites that we've measured at. We've got much more data than this, different commodities, but you can see the green, the yellow and the red, and on the left you can see the legend. Low emissions, 0.2% of nitrogen is emitted as nitrous oxide N per kilogram of N applied. Medium and then high. High emission areas tend to be in the higher rainfall clay soils of Australia, and you can see the sugarcane areas up there on the coast of Queensland. The majority of the grains region either in the green or in the yellow. And I've included this slide because the key to this is you fertilise to optimise. The optimal nitrogen rate must be when your yield plateaus. Many people in the grains industry use the APSIM model, and you can see here quite clearly, and it's been well calibrated and validated with all our data. You can see the top slide there, grain yield in black, and then the emissions are in red, the lines, and you can just see the yield plateauing out and the emissions increasing, okay? Again, the same example for Kingsthorpe, Tamworth. You can head down Wagga, and not as much so in Hamilton, higher rainfall, but this plateauing of yield, which is what you'll see when you've applied enough N, that's when your nitrous oxide emissions increase. So really, the agronomic and the environmental benefits of these come together. You apply enough N to get your optimal yield, and that's where the nitrous oxide emissions will be manageable. It's when you go over that N rate, go into a higher N rate, is the problems occur in terms of, one, profitability, because you've over applied, and two, environmental aspects and environmental pollution through greenhouse gas emissions such as nitrous oxide. This is the mantra. You would have all heard this. It's the global mantra: right product, right rate, at the right time, the right placement. But as we all know, many of these things, potentially the right time and the right placement, are difficult aspects to actually implement. It depends on the weather at the time, depends on the equipment you have. The right rate, again, that depends on how much nitrogen you've got there in the first place and how it is managed, the native soil N that's been carried over. But again, soil testing at the start of the season is critical to work through this. Right product, there's more work going on in this at the moment. That doesn't just mean urea versus ammonium nitrate or some other basic product. It means these enhanced efficiency fertilizers. The only issue with them at the moment is their value in terms of yield is not jumping out as being highly significant. Some do operate better than others when it comes to yield benefit. In terms of nitrous oxide, we're seeing big differences with some products, but you want to have both the environmental and the economic benefit. So that's the balancing act we're having at the moment with enhanced efficiency fertilizers. Thanks.